In the final unit of this week, we'll cover some of the general theory that underlies of what we have seen before. We are going to study a very general class of design patterns that come up almost everywhere in functional programming and also in reactive programming. The theoretical foundation of this class of design patterns is embodied in the concept of a monad. As we've seen, data structures with map and flat map are quite common. And in fact, there's a name that describes this class of data structure together with some algebraic laws that they should have. These data structures are called monads. A monad is a parametric type M with a type parameter T that has two operations, flat map and unit. And these operations also need to satisfy some laws. So you can see it in Scala as a trait, M, where M is the monad, T is the type parameter. It would have a flat map method of the type that you see here. So it takes an arbitrary type U as a parameter and a function that maps a T to a monad of U, and it gives you back the same monad applied to U. And besides flat map, there would also be the unit method. That unit method takes an element of type T and gives you an instance of the monad of T. In the literature, flat map is more commonly called bind, but in Scala we have flat map already as the established name, so I will continue to use that. Here are some examples of monad. List is a monad where unit is just the single element constructor. So given an x, I return the list that consists of just x. Similarly, set is a monad where unit of x is set of x. Option is a monad where unit is sum. So unit of x would be I have an element and here it is. And the random value generators that we've seen in the last unit, they're also a monad where unit of x is the single generator, single of x. As you've seen, flat map was available as an operation on each of these types, whereas the unit in Scala is different for each monad. Quite often it's just the name of the monad type applied to an argument, but sometimes it's different. For instance, for generator we use single, for option we use sum. So we've seen monads have the flat map operation. What about map? Well, in fact, map can be defined for every monad as a combination of flat map and unit. So the map applied to a monad with a function f would be flat map of first apply f to the argument x and then re-inject into the monad using unit. Another way to write this expression would be to use the and-then combinator in Scala that you have for function composition. So you could write m map f is m flat map of f and then unit. So you first apply the f function and then you apply the unit function to the result of that. Now in Scala we do not have a unit that we can call here because every monad has a different expression that gives their unit value. Therefore map is in Scala a primitive function that is also defined on every monad. To qualify as a monad, a type has to satisfy three laws that connect flat map and unit. Associativity is as usual a law about placing parentheses. Here the parentheses would be placed on the left-hand side, and here you see them placed on the right-hand side here. So we can alternatively either do the flat map here first or combine the two functions in the flat map and apply it to the monad. A domain where associativity is a bit easier to express is if we go from monads to monoids. Monoids is a simpler form of monads. It doesn't bind anything. So for instance, integers are a monoid and they are associative because x plus y plus z is the same thing as x plus y plus z in parentheses. So again, I can put the parentheses either to the left or to the right. The second law that needs to hold for a monad is called left unit. It says that if I inject into the monad using unit and then flat map with f, then the result is the same as simply applying f to the value x. The last law is right unit. It says that if I flat map with the unit constructor, I end up with the same monad value as before. Let's check the monad laws for an example type. I pick option for that. First thing we have to do is look at flat map for option. So what flat map should do is it should take an optional value. If that optional value is none, so we have nothing, then we keep none. If the optional value is something with a value x, we apply a given function to that value, and that will give us another optional value. Let's start to prove the left unit law. What we need to show here is that unit of x for option that was sum of x, as you know, flat map f is the same thing as f of x. So let's start with that expression, sum of x flat map f, and expand what flat map means. So flat map is this pattern match which says, well, if it's sum of x, then apply f to it. If it's none, keep on having none. Now that we can simplify, obviously, because we have a sum of x here, so it clearly matches the first pattern, and that would give us f of x as the result. So the first monad law holds. Let's look at the right unit law now. So the right unit law says that some optional value flat map with sum, which is the unit constructor, is the same thing as that optional value. So we start with the left-hand side, optional value flat map sum. We expand what flat map means, so we again have this pattern match which says, well, match if it's sum of x, then return now our function f is sum, so the function f here gets inserted here, so we return sum of x, and if it's none, then we return none. And that again simplifies to just opt, because we see that in each of the two branches of the pattern match, we return exactly this thing that we started with. So the right unit law holds also. Finally, we have to check the associative law. So here it is. We need to show that the sequence of the two flat maps, with the parentheses to the left, is the same thing as a flat map of a flat map with the parentheses to the right. So let's start with the left again. Here we have the sequence of the two flat maps. Here's what it expands to. So that line is the first flat map with the two pattern matches now on one line. And since the parentheses go to this, that's its expansion. So that result has to be subjected to the second flat map. So here we immediately follow the first pattern match with the second one, which now implements the flat map call with G instead of F before. So that's the expansion of this expression. Now what I do is I take the second pattern match, this one here, and I move it inside the two branches of the first one. So I know that the result of the first pattern match will be the selector of the second one. All I did here was to say, well, let's take each branch of the first pattern match and make it the selector of the second one. So I pulled this second selector in here and in here. That gives me this expression here. And that expression now in turn we can simplify. So let's look at the case none here first. So if the optional value is none, then we have the match none, match case sum y, g of y, case none, none. So obviously it would be the second pattern match that applies, and the whole expression simplifies to this one that you see here. So the second case is just if we get a none, we keep a none. Let's turn to the first case. So in the first case we say, well, if we got a sum of x, then we match f of x in turn. If we again get a sum of y, we give you g of y, and we keep a none. So what that is, if we look at things in reverse, it's just f of x flat map g. Because if we expand flat map g, then that expansion in turn gives us exactly that pattern match here. And if we look at that expression in turn, then we see that it's just another instance of a flat map. This time the flat map is with this function here. So we say, well, it's the function that says, given an x, it will return this expression here. So we get opt flat map x arrow f of x flat map g, and that's exactly the right-hand side of our original equation that we wanted to prove. So option is a monad because those three laws hold, as we have just shown. You might ask, well, why should I care about the monad laws? What significance do they have for programming practice? Well, one answer to that is that they give a justification for certain refactorings of for expressions that are quite intuitive. The associative law says essentially that one can inline nested for expressions. So if I have a for expression like that, where the first generator is in turn a for expression, what I can do is I can essentially inline the two generators here in one large for expression, and the result would always be the same, provided that the type in question satisfies the monad associativity law. The right unit law also has a significance for expressions. It essentially says that the trivial for expression here, where I generate x and immediately return it, is the same as the original value that you see here. For the left unit law, I haven't found an analog like that for expressions, so it seems that as what concerns behavior for expressions, only associativity and right unit is important. So here's another type that might or might not be a monad, we'll find out, and that type will be important in the later parts of this course. The type is named try, and it resembles option, except that instead of some and none, there are two cases which are named success and failure. The success case returns a value, just like sum does, but the failure case returns something, namely an exception. So the idea is that try will be used in cases where we want to propagate exceptions, not up the call stack, but say between different threads of different processes, or even between different computers. So in a sense, we want to bottle up an exception in a value that we can then freely pass around. Here's the definition of the try class. It's an abstract class try with a t parameter, just like option. The success case extends try and gives you simply a value of type t. The second case, failure, contains an exception and extends try of nothing. As you've seen in the functional programming course, nothing is the bottom type in Scala. Nothing doesn't have any value, and it typically refers to something that is either a missing value in the exception or a computation that does not return normally, because maybe the computation throws an exception or it loops infinitely. So the typical way to create try values is using try of expression. So you can wrap an arbitrary expression in a try, and that is achieved by making try an object in the standard library that has an apply method. So you've seen that anything that has an apply method can be applied, just like a function. The same holds for objects such as try. So what is the definition of this apply method? Well, it would take an expression, a computation, and return a try of the type of that computation. And what it would do is it would use a Java try, so a try that you know from the JVM, that's written now lowercase try. So we try to compute the value of expression and wrap it in a success. If the computation here throws an exception, that will be caught here in the block, and the exception will then be wrapped in a failure value and returned as a result. That happens for any exception that is non-fatal. Non-fatal is a fairly technical thing. Essentially, an exception is fatal if it doesn't make sense to export this beyond a single thread. There are a couple of exceptions that are, but the vast majority of all exceptions, both runtime exceptions and normal exceptions, are non-fatal. What's important here is that the expression is passed as a by name parameter, because otherwise, of course, we would already have a value here, so there wouldn't be a computation that could throw an exception. So that's why you have the type arrow t indicating call by name parameters here. Just like with option, try-valued computation can be composed in for expressions. So for instance, you could write for x taken from some computation, compute x, y taken from some computation, compute y, yield the result f applied to x and y, where f is some function that takes an x and a y value. So what that means is that if compute x and compute y both succeed, so they give you results success x and success y respectively, that would return a success value with the value f of xy. But if either computation fails with an exception, this will return failure with the first exception that got thrown. So to support this kind of notation, all we need to do is define map and flat map in the right way on the try type. Here are the definitions of flat map and map on the try type. Let's look at flat map first. So flat map takes a function from the domain T, gives us a try of u. And what it would do is it would say, well, if we start out with a success, so we have a value x, then let's apply f to x. That would give us the result value. But on the other hand, if the function f itself throws an exception, which is not fatal, then let's package this up in a failure value, because there's the principle that we will never leak non-fatal exceptions from a try computation. On the other hand, if we started out with already a failure and an exception, then that gets propagated into the result and returned here. What about map? So map just takes a simple function from t to u, and we have to wrap it up in a try. The way this is done is again pattern match on success and failure. If we have a success x, then let's apply f to x and submit it to the try constructor. So that again would, if f throws an exception, give us a failure. If f returns a value, then we would wrap that in a success. And as before, failures get propagated in the result. So if we look at the relationship between flat map and map, then that's what we have here. A try value mapped with a function f is the same thing as a flat map where the function f gets applied to x and then the result gets wrapped in a try, because that's how map was defined. And if I rewrite that expression here, I get t flat map f and then try. So t map f is the same thing as t flat map f and then try. So having map and flat map defined like this on try values suggests that try might be a monad where the unit is the try constructor itself. Is it? Possible answers would be yes, it is, or it isn't. And in that case, I would also like to know why it isn't. So it might not be a monad because the associative law fails, or the left unit or the right unit law fail, or maybe two or more monad laws fail. What do you think? Well, if we check the laws, then we find out that in fact the left unit law fails. Let's see why. So what's the left unit law for tries? It says that the unit, so that would be try, applied to an expression flat map a function f would have to be the same as f applied directly to the expression on the left. But it isn't. We have a non-equality here. And why is that? Well, the left-hand side here, as we've seen, will never raise a non-fatal exception. Neither try nor flat map would. Whereas, of course, the right-hand side will raise any exception that's thrown by either f or expression. So that means that the left unit law cannot possibly hold for a good implementation of try, and otherwise put that try, in a sense, trades one monad law for another law, which in this context is more useful. That other law, I call it the bulletproof principle, would be that an expression composed from try, map, and flat map will never throw a non-fatal exception. So to conclude, we've seen that for expressions are useful not only for collections. Many other types also define map, flat map, and with filter, and that enables them for for expressions. For expressions can be written over these types then. Examples we've seen were generator, option, and try. We've seen that many of the types that have a flat map and map functions are in fact monads. That means that we can also give a unit constructor, and we can verify that they satisfy the monad laws. You might ask, what about filter? We haven't seen filter so far. Well, it turns out that if these monads define also with filter and satisfy certain additional laws, they are called monads with zero, which is a somewhat richer category than monads. The three monad laws that we have seen give useful guidance in the design of library APIs, but as always, for every law, you also have to know when to break it. We've seen that the laws do apply to option and are very useful there, but they don't all apply to try. The left unit law fails. On the other hand, we've also seen that the left unit law itself doesn't really have a good explanation in terms of for expressions, so that would mean that while try is not a monad, it is still a type that can be used in a perfectly safe and reasonable way as the carrier type of a for expression.